This talk is based on the article Can Dimensional Anisotropy Satisfy Mach's Principle? In dimensional anisotropy, the dimensions of space depend on the object's location or orientation. Mach's principle states that the universe mass energy distribution determines local inertia. In other words, the motion of distant stars must influence the local state, and inversely. General relativity fails to satisfy this requirement because mass is unaffected by the gravitational field. The sport hammer throw can illustrate Mach's requirement. The thrower swings the hammer back and forth several complete rotations around a common center, and a careful balance is required. However, in the universe, entanglement changes cosmic balance. Einstein called entanglement spooky action in a distance because the compact dimensions form related spins independent of separation. Now, quantum mechanics shows that entanglement is a probabilistic division of the wave function. Upspin must balance downspin, creating local stress where this spin change happens. In turn, that stress generates interaction with the spatial field, making the changes irreversible, as shown on the bottom of the image. The irreversibility of interaction is often called time's flow. The contrasting transformations modify the field curvature, as shown in the S-shaped line. Downspin causes pressure, seen on the top, whereas upspin expands at the bottom of the curve. At its extreme, space itself transforms. Spatial expansion has the power of increasing dimensionality, forming hyperbolic geometry. Cold cosmic voids hide four-dimensional white holes. We can represent a hypercube in two dimensions. In contrast, spatial contraction can decrease the dimensionality, forming elliptic geometry. Therefore, three-dimensional Euclidean space, indicated on the image by the letter B, connects the four-dimensional and two-dimensional poles. The two-dimensional black hole is shown on the top, whereas the dimensional, the curly line on the bottom represents the expanding four-dimensional space. Furthermore, dimensional anisotropy modifies global mass energy distribution, satisfying Mach's principle. Like the finely maintained balance of the hammer throw, inertia reflects cosmic equilibrium. The object's position, shown by a star, corresponds to a freely hanging plum. Deviations in the plum's angle, which is the object's location, change the balance of the whole universe. Nevertheless, inertia is proportional to the object's mass and field strength, which is the topological distance from the black hole. Although the balance is most precarious in the vicinity of the black holes, the inertial mass grows infinitely there. In contrast, cosmic voids lack mass and thus represent the stable center of this cosmic structure. So we can demonstrate the universe by a balloon where black holes form its outer boundary, and the four-dimensional cosmic voids expand it continuously. The pole's prohibitive climates constrain biological life for the galactic regions, while more research is needed to explore these ideas and their implications. The hypothesis might shed light on the actual structure of the universe. For example, our conclusions describe the warped cosmic geometry suggested by the anti-de Sitter space conformal field theory known as ADS-CFT duality, which is the famous theory proposed by Maldacena and often represented by the hyperbolic tessellation on the right on this picture. You can find link to the article and to more videos on this topic in the description below.